Okay, I am going to cover chapter 6 today. I'm not covering the whole chapter, just the first part of the chapter. Let me go ahead and scroll down to the actual slide. I will start here. When we are communicating information about chemicals, we tend to use chemical formulas. Chemical formulas are used to represent the particles of an element or a compound, as it says right here, in written form. We use symbols and subscripts to denote the element present and the number of atoms of that element present. So we're told here the subscript number denotes or let us know how many atoms of that element are present. The format tends to be, I'll use X, A, Y, B. The B tends to be the number, the A and B tend to be the number, X and Y tend to be the symbol. The number tells us how many of the symbol before the number are present, okay? So in this made up equation I'm showing you, we have A number of X and then B number of Y. If the formula looks like this, where we have X sub 1, Y sub 1, or X sub nothing, Y sub nothing, that tells us that there's only one atom of that element if the subscript is omitted, okay? So we have 1 of X and 1 of Y. Okay, looking at H2O here, or water as the example, we can see in our example, we have 2 hydrogen atoms and 1 oxygen atom present. Now, we saw this before when dealing with the Lewis structure, but we're seeing this again in the context of naming compounds. In this formula here, we have Na and Cl, 1 of each. Remember, when the subscript is missing or appears missing or is 1, that just denotes or communicates as one of the elements before the number, okay? So I'm going to move on and talk about diatomic versus monoatomic elements. So we're told a majority of the elements that we know of in the periodic table actually exist as single atoms. Now there's some that are able to exist as multiple atoms, and we're going to get to that. Example of these essentially are helium and lithium. Helium and lithium, when you're writing the formula of helium, which is He, lithium, Li, the way you're writing the formula communicates that this element exists in uncombined form. So we're told right here, the formula that you wrote reflects that the basic unit of that element, of one particle of that element, exists in an uncombined atom, okay? On the other hand, we do have diatomic, monoatomic, triatomic, polyatomics. Let me take a step back a little bit. Monoatomic elements, these elements are like helium and lithium. Helium, by the way, is a gas. When you see helium in nature and you're studying the fundamental particles, each helium exists as one individual atom of helium, shown right here, okay? These are individual atoms of helium. It's an example showing you that. Or the other example we saw here was lithium, but to be specific, lithium is actually a solid. So this would not be an accurate way of showing lithium. You will show lithium atoms as individual atoms, but lithium is a solid, so these atoms will be packed together to make a solid. But it's implied and understood that each building block or fundamental unit of lithium is a single atom, okay? So monoatomic elements have atoms that exist in uncombined forms, singly, okay? Versus diatomic molecules, they're called molecules because they combine together. You have 2 atoms combined together, and these are 2 atoms of the same element combined together to make a molecule. When atoms are by themselves, they're called atoms. When they're combined together, they get a new name, which is a molecule. So here we're seeing examples of diatomic molecules. And this part here is a little tricky because technically they're still both elements. But when you find this element in nature, naturally, you see two units combined together to represent the basic form of that element. Once again, two units combined together. Two units combined together. My students taught me Brinkelhoff, and this is Brinkelhoff. This is an acronym that describes the elements that tend to exist as diatomic molecules in their fundamental form. So Br2, that will be bromine, I2 iodine, N2 nitrogen, Cl2 chlorine, H2 hydrogen, O2 oxygen, and then F2 fluorine. Okay, these are the elements in the periodic table when they're found in nature in their basic form, exist as two atoms tied together to make a molecule. When I say tied together, I mean connected chemically, right? To make a molecule. Before these molecules react, they break down into the atomic form and then they react, okay? But you see them here in the periodic table. Remember, anytime you're asked to write a balanced equation and you're told you had elemental hydrogen or hydrogen gas, you will need to write H2 because it's understood. In its basic form, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine will all exist as diatomic molecule, okay? Molecules. Or if you had, like we discussed before, helium, lithium, sodium, group 8 elements, they will all exist as monoatomic molecules. Monoatomic atoms, okay? Now we do have others such as phosphorus. Phosphorus actually exists as 4 tetraatomic molecules. It will have 4 units in the tetrahedral geometry. Yeah. And then we have sulfur. Sulfur exists as 8 atoms tied together. Okay, so you have 8, 1, 2, 3, 4, 5, 6, 7, 8 tied together to make one molecule of sulfur. When you have sulfur by itself, you see 8 atoms tied together or connected together. With phosphorus, you will see 4 atoms connected together, okay? But you are required to know the monoatomic elements, which is pretty much all of them, except for the diatomics, right? So you want to make sure you have a list of the diatomic elements and you memorize that list, Brinkelhoff. Moving on. Over here, we're being told, since this chapter is about naming, we're always going to go back to naming compounds or naming elements. We're told here, write the chemical formulas of chlorine, argon, bromine, and krypton. This has been done for you. Remember, the assumption here is this is elemental chlorine. You write it as Cl2 because it's part of the Brinkelhoff family. Argon is not, so you write it as Ar. You find the symbol from the periodic table. Bromine, part of that Brinkelhoff family, so once again, you got to put Br2. Krypton, not part of the family of Brinkelhoff, so you put Kr, no sub 2, okay? Since we had answers here and you're able to see the answers before you even thought about the question, I went ahead and added some questions in the PowerPoint slide to give you a little bit more practice. So over here, let's see. Let's see if you can figure out the answer before I write down the symbol. Vanadium, it's going to be V, is not Brinkelhoff. Oxygen is O in the Brinkelhoff, so it'll be O2, right? Magnesium is not in Brinkelhoff, Mg. Fluorine is an F in the Brinkelhoff, F2. Iron is not in the Brinkelhoff, Fe. Okay, so once again, please notice all the symbols of the element in the Brinkelhoff family, you have to write that symbol sub 2 because these tend to exist as diatomic elements in nature. The rest are monoatomic, except for the special cases we talked about here, okay, the SA and P4. Okay, so let's go ahead and move on from here. But when you're dealing with the compound, you want to look at the compound and kind of break it apart into the component elements that made up that compound. So you want to answer the question, is the first element a metal? Or is the first element a nonmetal? What about the second element? Okay, so we're going to go into all that stuff, but for right now, we want to make sure we're clear on this. In the periodic table, we essentially have a majority of the elements being metals, and then the minority being nonmetals. Now, when we look around, as we see more nonmetals, right, in living things, carbon is the most abundant element because it's in all living things, carbon, organic, all this stuff, right? So we have more nonmetals, but we have more types of metals. So the zigzag here separates the nonmetals from the metals. Okay, as you can see, if the metals are essentially the blues, my favorite color, the nonmetals are yellow. And then you have the green here. So the green is selected to communicate a point. In the green region right here, we have an overlap. This is where we have the metalloids. The metalloids are like those people who live on the border of two different countries. They tend to assimilate, mix up the culture of both sides of the border. Okay, so here we have these elements that assimilate. They represent both sides of the border, of the boundary, the zigzag line. So these are called metalloids, having both metal and non-metallic properties. These are very popular in technology in Silicon Valley, right? In the semiconductor industry, especially silicon, right? So I used to ask this question a year ago, what is silicon known for? And I used to get the answer, semiconductor. Now when I ask this question, I get a different answer. I'll leave it at that. Okay, so moving on. We're back to classifying metals from nonmetals with the goal of naming a compound. You want to classify before you name. Okay, it's important for us to know, is our metal in group 1A, or is it in 2A, or is it in 3A? We need to know, is our metal an A metal? I mean a group A metal, okay? So we want to know, is it a group A metal, or is it a group B metal? Why is that important? Why do we have to distinguish one from the other? The way we end up naming the compound varies based on the group we assign the metal to, okay? So we're told here, names and formulas of non-atomic ions. These are group 1A/group 1, group 2A/group 2, metals and nonmetals, okay? So we're trying to deal with the metals first, and then we'll deal with the nonmetals later. We're kind of going back a little bit and defining an ion, okay? Let me drink some water. It's a little warm in here. Okay. For the ion, we're told an ion, so we're trying to name, right, an ion. An ion is essentially formed from a single, and we're talking about monoatomic ions. So an ion formed from a single atom. The special name here is monoatomic ion, specific name, okay? Ion formed from a single element. So they kind of quickly review for us here. Okay, an ion formed from a single atom. So we're defining an ion. An ion is an atom or chemically bonded group of atoms that can electrically charge because of an excess or deficiency of electrons compared with protons. Wow, a very interesting definition. What they're saying here is an ion essentially has excess protons or excess electrons. Okay, that's what we're trying to say. They went about it a very, very interesting way. But yes, ultimately an ion can actually have an electric charge because it has an excess charge, right? Positive charge or negative charge. So we're told here the cation is positively charged because remember it has excess protons. So it lost electrons, so it ends up with too many protons compared to electrons. Here, an ion is negatively charged because it has excess electrons. Okay, It didn't lose electrons, but it gained extra electrons. So now it finds itself having extra electrons. Okay. Rules for naming monatomic ions depend on two things: the location of the element that's producing the ion in the periodic table. Now, this can be generally, is it a metal or non-metal? Okay. Are we dealing with group 1, group 2, group 3, or group 4, group 5, group 6, or group 7? Okay. Next thing, if it's a metal, is it a main group metal? This is a group A, or is it a transition metal? Group B. Okay. So you want to kind of simmer it down, or you want to look at your molecule and then you want to decide, is the molecule you're looking at, the first element in the compound, is that a group 1A metal, a group 2A metal, if the first element is a metal? If it's a non-metal, then you're using a whole different nomenclature system. So looking at this right here, okay, looking at this rules right here, we are going to be starting with naming cations, okay? We will start with naming cations. And the way I've written this, I wrote this ahead of time. We're going to start with group 1A cations. Remember, cations, not cations. These are positively charged. And just in case you have forgotten, these are metals, right? Positively charged ions. We're going to start with the metals. We'll start with group 1A, metals, group 2A, metals, and group 3A, metals. And these are all cations because they're positively charged metals. These tend to have a fixed charge. When you're working on your lab will introduce you to two main categories of metals. The ones that have a fixed charge, they have the same charge no matter where you see them all the time. When they're existing in an ionic form, they have the same charge. For example, potassium ion, sodium ion. Potassium ion always has a charge of +1. Sodium ion always has a charge of +1, okay? So let me go straight into the examples since I'm already talking about them. We're looking at group A. Remember group A, these have the same charge all the time. And they're called fixed charges. Fixed because they're predictable, always known, right? Fixed charges, they don't change. When you're trying to name the cation essentially has the same name as the element. Sometimes they'll say ion to kind of distinguish the two, right? But the cation name is equal to the element name. To give you an example here, remember cation, sometimes books will use the word ion. So I'm going to go ahead and use the word ion just to be clear, okay? The element name is essentially the cation name. I give you some examples here of group 1A cations. Remember, these have an excess of positive charges or proton. Okay, lithium. This is going to be lithium ion. Remember, the element is called lithium metal, but because it's an ion, you can just say lithium to be lazy, or you can say lithium ion to communicate better, okay? And then this element here is called sodium, and the ion is called sodium ion. When you're naming the sodium component in the compound, you don't want to use the name ion, but when it's by itself, you can say sodium ion. And here we have potassium ion, okay? So for whatever reason, if you were asked to name an ion by itself, you would just name, if the ion is a group 1A or any of the A group cations, the name of the element is the same thing as the name of the cation, okay? So I'm going to go ahead and move on over here and go to group 2A. I picked some examples here. Once again, group 2A, we're looking at Be. Once again, the elemental name is the ion name, but to be more clear, I'll use the term ion. So here we have beryllium. I feel like I misspelled that. Beryllium ion, okay? And then here we have magnesium, same name as the element, ion. Now, of course, if you're naming the element, you will leave out the word ion, right? Because then at that point, the element has no charge. There's no need for the word ion. And then this would be calcium ion, okay? And this is how you will name these group 2A cations. And this is group 1A cations, okay? Let's see what we have for group 3A. For group 3A, the most common cation we have is aluminum. So this will be aluminum. I'm spelling it the American way versus where I came from. It was aluminum. Okay, aluminum ion. Okay, so remember, these charges that we see here, if you're wondering, you go back to the periodic table. Remember, this is group 1A, the elements right here. So all of these will have a similar charge, right? And then this column right here is group 2A. I just named a few elements or a few ions from group 1A, did the same thing with group 2A ions. Then I went ahead and named the metal ion in group 3A. Now here's the thing, okay? Actually, the metal ion in group 3A is in the bottom. Remember the metals are the blue ones, right? So here's the thing, though. Here's the caveat. Are there other metals in group 3A? Yes, but I'm going to talk about them later on because they don't fit this little conversation we're having right now. Remember that the nonmetals are the yellows. So technically, the hydrogen here is classified as a nonmetal, okay? It does get a little complicated, y'all, but yeah, it's nonmetal. So let me go back to where I was and continue from there before I get all caught up in stuff. Okay, so that was the intro to naming group A group ions. Now we're looking at B group ions. With B group ions, let's go back to the periodic table. I just thought about something I forgot to mention earlier. Okay, so I'm going to go through and show you which metals are A block and which ones are B block, okay? So we got group 1A here, we got group 2A here. Remember, essentially, these make up the S block, okay? Now, we do have a metal, that's an A metal in group 3A. And this is technically part of the P block, right? And that's aluminum. Now, we do have other metals down here. These four metals down here behave like metals in the B group, okay? Remember, these are called B because the group numbers are essentially labeled 1B, 2B, 3B, all the way to 8B. And remember, this group here is labeled B because they have variable charges, as in different charges, while the A metals have fixed charges. So every time we see them, they have the same charges, okay? Including the one right here, aluminum. These on the bottom here will have different charges depending on what non-metal they're combined with. Their situation defines their charges. They have the ability to lose 1, 2, 3, many electrons versus these right here in 1A will always lose 1 electron. So one in 2A will always lose 2 electrons. And then aluminum will always lose 3 electrons all the time. No question about that, okay? So let me go ahead and down here. So what I have here is a list of examples of group B metals. Remember, these are group B metals. Group B metals are usually found in the D and the F block. Now, remember, we saw that some in the bottom of the P block behave like B metals, but they're technically A metals, right? Remember, A metals have got a fixed charge, the same charge all the time. B metals depends on what they're combined with. The nonmetals help us to figure out what the charge in the metal is, okay? So because of all this ambiguousness in the B metal, when it comes to naming the B metal, imagine being on the phone, right? And you're on the phone trying to describe to somebody, hey, can you get me this compound versus this compound, okay? The first versus the second. Okay, so you're probably wondering, well, just say FeCl3 versus FeCl2. We don't say things that way. The way things are said in chemistry is The metal here has a charge of +3 or 3+. Okay, remember you crisscross to get the compound, and so the metal is Fe3+, the non-metal is Cl-. The metal here is Fe2+, the non-metal is Cl-. Okay, so with that being the case, you would say on the phone, hey, Bob, you're calling Bob, can you get me some iron 3 chloride versus the iron 2 chloride? You know, I have iron 2 chloride, but the experiment I'm trying to work on calls for iron 3 chloride, right? So that Bob over there will be like, oh, he wants iron 3 chloride, not iron 2 chloride. I know y'all will be like, well, just say FeCl3 versus FeCl2. That's not how scientists communicate, okay? This is the newer way. The old school way, yeah, there's an old school way of saying this is, if you've seen this somewhere, ferric is a term that describes iron 3. Ferrous is iron 2. Kind of like a ferret, but not a ferret. Ferrous and ferric, okay? So ferric is, if it ends with IC, it tends to be a higher positive charge with versus the OUS, a lower positive charge, okay? If you've seen that before anywhere out there. Okay, so backtrack a little bit with the naming rules, and let's go back and see how we can learn nomenclature. Okay, in naming this now, remember this is group B. In group B, you have to specify the charge in the name. So the name will have these parts. The element name will remain. You got to get the charge on the ion because it can't be implied because it could be one or the other or the other. And then you have to, well, you can include the word ion. Okay, so for this, V stands for vanadium. And then 5 is a charge. You will write it in Roman numbers. I just remembered. I'm sorry. I kind of have to go back because I keep remembering things randomly. I stands for 1 in Roman numbers, and then 2I stands for 2, 3I stands for 3, IV stands for 4, like King Henry the Fourth, you know. V stands for 5, VI stands for 6, VII stands for 7, VIII stands for 8. When I was in school, our grade levels were written like this. I think they were low-key trying to get us to learn these numbers because they're like, well, where is your classroom? We're right there. And then it had a number and a letter. What is it? Well, 111A. That's your classroom. So you had to learn it. You had to learn what it stood for. And on your notebook, you wrote your name and then the classroom. Them teachers were smart. Okay, anyway. IX stands for 9. Of course, you all know iPhone X, right? iPhone 10. They kind of say that back in their retro. This stands for 10, right? Anyway, you want to know these Roman numbers because when you're writing the numbers of the charge in parentheses, you have to use Roman numbers. So we got vanadium 5, ion, okay? Next one, chromium. CR stands for chromium, 1, 2, 3. You can write it like this or write it like, you know, that, either way. Chromium 3, ion. And then this is iron 2, iron, right? Iron 2, iron. I've seen some books not use parentheses, but the more common way I see this written out is using parentheses. Okay. And then we got copper. This is the symbol for Cu. Then here we have 1, iron. Then we have CO, which is cobalt. 2, iron. And then we got iron. Oh, I'm writing the symbol again. My bad. Iron 3, iron. Okay. That helps us distinguish the iron 3 from the iron 2. Okay. Okay. I already told you guys before. Oh, here's the list. Okay. Remember, I told you the majority of the A metals are in the S block. and the P block. But if you look at the bottom of aluminum, there are other metal ions there, but I didn't call them A metal ions. And this is these right here. They're still in the P block, which should technically make them A metals, but they behave like B metals. So the way I like to label these is, these are technically group A, and I put two X's here, or star, star. Let's call these star, okay? So there'll be group A, star, star. And these are tin, lead, bismuth, and antimony, okay? When you are writing these in ion form, you have to specify the charge because they may have more than one charge. No, not they may, they do have more than one charge. Ergo, though they are placed in the periodic table where it's in the P block, underneath group 3A and group 4A, they actually behave like they were in the D block, okay? Okay, other exceptions. You do have element. Okay, these are exceptions from A group, okay, just to be clear. We have exceptions from the B group. Okay, these are metals in the B group. We agree. Okay, silver is in that B group. Zinc is in that B group. Okay, so going back to the periodic table, I know I don't have one here that shows you all the symbols and stuff, but let me try to draw them in here like they were actually here from the beginning. We got zinc right here, we got silver right here, these two right here, okay? They're clearly in the D block, right? They're clearly in the B group, but when you name them, you can't include the charge, because even though they are in the B group, they don't have more than one charge. These have only one charge, okay? So by this point, you're probably saying, oh, these rules and the exceptions, y'all. When it was my time, that's exactly, I mean, maybe y'all are all chill and laid back, but that's not me. When I was learning this, I was like, oh, another exception. I'm not gonna remember this. It's gonna be so hard, you know? I figured it out eventually. But here's the thing, okay? When you're naming this, silver will always be +1. So here you will write silver ion. And zinc will always be +2. So you just write zinc ion. And you don't write silver 1 or zinc 2 because it's implied. It's always going to be silver 1. It's always going to be zinc 2. So there's no need to emphasize it. Over here, remember, going back here, you got to emphasize this because it can be tin 4 or it can be tin 2, right? Lead can be 4, lead can be 2, bismuth can be 3, it can be 5. Antimony can be 3 or 5. You never know, so you got to specify based on the charge. Okay. Let me see, I can keep going for a little while because I do have a session coming up. Anyway, when we are writing the name and the formulas of non-atomic ions, okay, looking at group 1A or 2A, so these are ions. We already did that part, right? The first part talking about the metals. We're now looking at actually the format of writing the name. So it says here, writing, okay, let me do this over again. Writing the name and formula of monoatomic cation, we just went over that. It says right here, name of element followed by the word ion. Just like I said, right? When you have a monoatomic ion, just name the element followed by the word ion. So just in case I wasn't clear, monoatomic, I mentioned this before, just means the formula of an ion is made up of one element. If you look at the periodic table, you will see the formula of the element by itself, somewhere in the periodic table, okay? When we look at polyatomic, we'll see a combination of more than one element to make that ion. So they walk you through this. Now I want us to look at monoatomic anions. Once again, monoatomic, made from one element. And now we're looking at the non-metal, okay? So we're looking at the right side of the periodic table, the side that was yellow, and these are from nonmetals. We mentioned before, we don't have too many of these. We have more in numbers, but not more in types. So going back to the periodic table, let's see right here in the periodic table, see, our nonmetals are this yellow section right here. So I'm about to go over the rules on how to name these nonmetals, okay? If they're in ionic form. So how do we name these nonmetals in ionic form? Let me see. Oh, so I kind of broke it down, right? I have examples here, and I started with, oh, by the way, I skipped over group 4. That was intentional. Most of the time, group 4, let me write this down somewhere. Group 4 elements tend to share electrons, not form ions, okay? Remember, to form an ion, this is a quick recap. To form an ion, you have to either lose electrons to become positive or gain electrons to become negative. But group 4 elements are not really losing or gaining, they're just sharing. So they're not forming, they're kind of bypassing the formation of ions. So for that reason, we don't commonly find them as ions because they've kind of risen above, not really. They just don't do that. It's not common for them. Do we have group 4 ions? Yes. Is it very common? No. Okay. So for that reason, I skipped over and went to group 5. So once again, I need to be more specific here, right? Group 5A, group 6A, group 7A. Okay. So we are here. So N3 minus is the charge, the likely charge of group 5A elements. So how do we get N3 N3 minus? Okay. Remember, you all learned this before, right? Remember, going back to this, for the metals, I need to recap. For the metals, 1A has a charge of +1. The charge matches the group number. 2A has a charge of +2. 3A has a charge of +3. 4A is kind of complicated. It doesn't really gain or lose 4 electrons. 5A has a charge of -3. 6A has a charge of -2. 7A has a charge of -1. Okay, so if you want a mathematical way of figuring out the charge on 5, 6, 7, I just look at it like a palindrome. +1, +2, +3, skip over 4, -3, -2, -1. Right? To me, that's a lot easier than doing math, but I've seen it done before. People prefer this. Some people do, where they say for group 5A, take 5 minus 8. Remember, 8 is the octet, you get the charge -3. Group 6A, take 6 minus 8, you get -2. It's a neat little thing, but I don't see it as necessary. 7 minus 8 equal -1. But my goal is to equip you with whatever you need to succeed, right? So I'm going to show you ways I'm not crazy about. And I'm going to complain about it the whole time I'm teaching you, but you get to pick the tools you need to succeed, right? That's my goal here. Teach you tools to succeed. Okay, where was I before I went talking about random things? Okay, let me see. I'm picking up where I left off. Okay, so we're naming monoatomic anions, and as I mentioned before, these are the nonmetals. To name them, we have to review STEM names. So I'm assuming that STEM names have either not been covered, at least I know I haven't covered them, or if you've covered it, don't worry about it. It's going to be a review for you. All the elements, well, yeah, the elements tend to have common STEM names, okay? Let me take a step back. So, for example, we have nitrogen for the element N that has a symbol N. We have sulfur for the element that has a symbol S. We have, let's see, hydrogen for the element that has a symbol H by itself when you're represented in the diatomic form, H2. And all of these elements have STEM names. And the STEM names or the STEM words are the parts of their name, the letters in their names that appear over and over and over again, sometimes in modified forms, okay? So for nitrogen, the stem word is nitra, as an N-I-T-R. For sulfur, it is sulf, as an S-U-L-F. For hydrogen, it's hydra, okay? So sometimes it's hydride or hydro, but you get the idea, right? So all of these elements do have stem components in their names that tend to appear over and over again. They're not necessarily prefixes because they're a part of the name, but understanding that we want to use the stem components of the names of these anions. So for nitrogen, once again, it's N-I-T-R, nitra, that's the stem name or the stem word that we use for nitrogen. For phosphorus, we're going to use phosp, okay? And so we're building the name of the anion from the stem name, okay? So nitra, to get the anion name, you're going to take the stem name and add IDE to it. Okay, so let me go back here. We're taking the stem name and adding IDE, and that helps us to get the anion name. So for nitra, we add IDE and we get nitride. Nitride is the name of the anion N3-. So the anion form of nitrogen. And then for phosphorus, which has that formula, we have the name phosp, then you add IDE. So stem ide is the format we're using, we get phosphide. Notice that these anions I have written here, these are monoatomic anions. What does that mean? These are anions made up by an individual element, a single element, not a group of elements, okay? Once I get to the polyatomics, you will see the difference. Continue. So, oh, by the way, that was group 5A. So moving on to group 6A, I now see a set of common anions. Remember, group 6A anions have a charge of -2. So starting with the stem word, so I'm continuing the format I had here. I'm starting the stem word, then I'm going to look at the stem ide. Excuse my congestion. I've been a little congested. That's why I do sound a little nasally, but I'm trying to get this video out, so please bear with me. Okay. For oxygen, the stem word is ox. For sulfur, like I mentioned before, the stem word is sulf. For selenium, the stem word is selene. Not like Celine Dion. Well, I was thinking about it. Okay, so to construct or put together the anion word, we add IDE, so we get oxide. Here we get sulfide. And for selenium, we get selenide. And so these are essentially the stem names for these anions, okay? And then finally, I have group 7 anions. Now remember, the anions in group 7 have a charge of -1. If you're wondering again, well, remember the group number -8 gives you the charge. Group number -8 gives you the charge -2. Group number -8 gives you the charge -1. Okay. Okay. Next thing is looking at this list here. For fluorine, the stem word is fluor. Okay. For chlorine is chlor. For bromine is brom or brome. And then iodine is iod. Okay, so remember, to get the anion name, you're going to use the stem ide format. So add the IDE to the stem name. So this would be fluoride, chloride, bromide, iodide. Okay, and this will help you in determining the anion names for the monoatomic anions, okay? This is very different from when you're dealing with the polyatomic anions. Those tend to have many atoms. Oops, what am I doing? Well, this is just a review of what I showed you earlier, right? That when you're looking at the charges, so it says write the names of these. So remember, when it comes to the charge of the ion, okay, the charge of the cation charge is equal to group number. That's what I just erased. anion charge is equal to group number minus 8, okay? So bromine is in group 7, that's why it's -1. Barium is in group 2, that's why it's +2. So when you're naming it, of course, you say bromide ion, and this is very important in your homework. In your homework, I think you have to type the word ion in, or else you get your answer wrong. Barium, Ba2 plus, has to be barium ion. Potassium, K plus, potassium ion. See, they're already getting lazy, right? The same potassium, but you have to write potassium ion. The context defines the answer, right? Fluoride ions, you write fluoride ions. Sometimes for the positive ions, the cation ions, they leave the word ion out, but you want to know it's an ion based on the context of the conversation, okay, or what you're reading. Okay, so now we're looking at names and formulas for monoatomic ions, additional metals. So here we're looking at, actually this is a summary of what I talked to you guys about, right? Naming the metals, metal ions that have variable charges. So I'm not gonna go into all this stuff here. This is an example of the common polyatomic ions. And when I showed you guys earlier, you want to, by the way, before I get off this list, you want to make sure you have this list. Copy this somewhere, have a screenshot of it. I would say, copy it in your notebook. Take some time to copy this down. That way, as you're writing it down, your brain is processing what you're writing. Stack elements that have the same, ions that have the same elements, or at least starting elements together. So what I mean by that is, if you look at this list, right, this is not alphabetical, but they try to put elements that are similar together, right? At least the ions. Okay, before we look at the list we have, let's look at what we're looking at here, right? You do have some common polyatomic ions. So polyatomic ions, for the most part, you're looking at ions that contains more than one element. Sometimes it's multiple of the same element, like we're seeing right here in mercury 1. This is called mercury 1, by the way. I know it's weird. You're wondering, how is Hg2 1 mercury? And then it's 2 plus. What's up with that? This is one of those scenarios, right? I know you're like sighing heavy. That's what I did, and I'm still sighing heavy, right? Where the mercury ion Hg1 exists as a diionic, but it exists in 2 ions combined together. That's how they exist in nature. So essentially, if you're wondering how this is named mercury 1, imagine the Hg that's positive connected to another Hg that's positive. So when you consolidate that, you get Hg2, 2 plus, and they exist together as a unit. But it's still called mercury 1 because when this unit reacts, it reacts as mercury 1. Remember, even though the form these diatomics or diionics are when they're by themselves, are not the same as the form they take when they're about to react. I know what I'm trying to communicate. I'm struggling to find the words to communicate, but remember, the mercury 1 ion breaks apart from its other ion right before it reacts. So we are naming it in the form it reacts, not in the form that it is, okay? If that makes sense. If it doesn't make sense, just gloss over and fast forward this part. But that's how it is. Okay, moving on. You want to know the name of ammonium. Ammonium ion is a very common ion that we talk about. Ammonium, you can see here, is made up of nitrogen attached to 4 hydrogens, right? So it's called polyatomic because poly means many, atomic means elements or atoms that represent elements. So you have an ion made up of many elements. So you have NH4. Okay, so this is what I was talking about before, right? I'm not going to spend too much time in the naming of this, but please notice what these 2 polyatomic ions have in common is they have nitrogen, right? From nitrogen, we get the name of the prefix nitrate, the stem word, sorry, not nitrate. We get the stem word nitra, right? From the nitrogen part. And then you can see the first polyatomic ion has 2 oxygens. The second one has 3 oxygens. So when it comes to the "ite" and the "ate," these are suffixes in the name. So the prefix is the nitro part, right? The suffix is the second part that is common. The suffix represents a relative number of oxygen, not a specific number. "Ite," polyatomics that end with "ite" tend to have less oxygen. So where do I write this? I need to write this somewhere. Let me write it down here. Polyatomic ions with oxygen, which is the majority of them, I should say, with relatively less oxygen tend to have the ITE suffix. Okay, so the last three letters of the name of that polyatomic ion that contains oxygen is usually called the oxyanion. So that is essentially the oxyanion. So this is the anion that has oxygen. That's an easier way to describe it. The oxyanion that has less oxygen. So oxyanion with less oxygen has a name that ends with ITE, okay? So just to notice that, let's go ahead and go through. So here, because this has less oxygen, the name ends with ITE, nitrite. This one here is going to be nitrate, okay? Here, remember sulf, okay? So sulf in honor of sulfur, and then ite, less oxygen. It isn't saying two oxygen, it's just saying less oxygen. So we have SS, sulfite, and then sulfate. Okay, so if you're wondering, wait a minute, I already forgotten, I'm going back here and I've forgotten what's going on. Let me give you a quick overview that will probably help you. Monoatomic anions. The suffix is IDE. This is not 100% of the time, but this is the common. So commonly, this is what we see, okay, in common. Commonly, monoatomic anions have a suffix that ends in IDE, okay? With the I should say, with the oxyanions, remember, these are going to be polyatomic. Polyatomic. That means they have some kind of atom and oxygen. Well, these, and of course, the anions we're talking about, their suffix changes, right? We have a suffix A that ends with ITE, and this is just communicating less oxygen. It's always relative. And then you have another suffix that ends with ATE, and this is more oxygen. It doesn't mean two oxygen or three oxygen, just whatever. So when I was studying this as a student, I was pacing back and forth before we had the exam. We had a common ion exam in the majors class. So I'll be pacing back and forth, holding a sheet of paper that has a list. I'll be saying IDE, monoatomic anions. So IDE, these are the ones that you find in the periodic table. Okay, so IDE, these are the regular anions, like oxide, phosphide, nitride, sulfide. They don't have any additional thing, no oxygen, nothing. And then the ones with the eights and the ites, I said the eights have more oxygen, the ites have less oxygen. So this wasn't helping me to essentially name the individual elements, but it was helping me to somewhat categorize them and pack them and sort them out in my head, okay? And this may be useful, it may not be, and if it's not, just forward through it. You had that right, okay? So let's go through and see if we can find. Now remember, all these little caveats I'm giving you, they don't cover everything. They just kind of help you sort things into major groups, but it doesn't cover every scenario, okay? So let's see if we can find some more eights and ites. Go back here, okay. Not the situation here. No, not on the left. Let me see on the, oh, here, look at this. Cl, 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 ClO, 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 ClO. And this situation here has got, let's see, different number of oxygens. So what I do with this situation here is I actually, since there is 4 ClO types of anions, what I do is I focus on the middle 2, okay? And use that as my starting point. Then I go to the one above and the one below. In the middle 2, you can see, first of all, from all of these, right? The non-metal that's not oxygen is chlorine. So here, of course, we're going to have chlor, and then chlor. And the chlor is the stem word that represents chlorine, okay? So starting with the middle 2, the top one, ClO2 minus, has relatively less oxygen than the one below. So this will have the ITE because it has 1 less oxygen. The one below has 1 more oxygen, so relatively, the ith is always 1, it's not always 1 less, it's always less. Ooh, what was I gonna do? Sorry, it's always less than the 8. So we got the 8 to represent relatively more oxygen. Chlorite, less oxygen. Chlorate, more oxygen. In this case, it happens to be 1. Now, I'm always asked, well, what's the easiest way to remember this? I'm like, when it comes to the formula, you just memorize them. What I do, I try to stack them based on how similar they are, and I go from there. Like, I always learn these 4 together, and I always remember them together. It makes it so much easier. I can remember them alone, but because I know it now, but when I was learning them, I learned them all together as a set, like they came together, okay? Okay, so remember, ITE means less oxygen, ATE means more oxygen. What happens when you have less than the less, lower than less? In biology, they use the prefixes hypotonic to describe a low concentration solution, and then hypertonic to describe a high concentration solution. So hyperbole in math, meaning, big person's hyper, a lot of energy. Hypertonic, high concentration. You get the idea that hyper is used to describe more than, excessive. Well, here they don't use the term hyper, but they use the per part from hyper. Per in chemistry means more, okay? So perchlor, the prefix per is added to chlorine to signify, but it's not even more chlorine. I know that's kind of confusing, but per is talking about the 8 part. I wonder why, I won't confuse you guys, but it's called perchlorate. So perchlorate has 1 more oxygen than just a regular chlorate, okay? But when it comes to the ite, you have hypochlorite, which has 1 less. Remember, hypo signifies less. We're talking about oxygen here. So hypochlorite has 1 less oxygen than chlorite, okay? This is where we are. Let me see what else. So we have permanganate. Per, once again, standing for 4 oxygens, many oxygens, right? In this case here, you do have chromate, and then the chromates kind of combine with each other, but it's not as simple as you think it is. It combines with each other in the process, losing 1 oxygen, but that's how we get the dichromate. Some of this stuff is don't even worry about it. We have oxygen and we have peroxide, per once again meaning more oxygen here. So the nomenclature isn't logical to where they're consistent in the way they name it, because they didn't say perchromate here. They didn't say peroxalate. They didn't say that, right? So please don't try to use logic to memorize this. Just memorize it, okay? Because the way they're naming it isn't consistent. You want to make sure you know carbonate and all that stuff. So anyway, I'm done with this page, y'all. Please go through, have this list with you. You're going to be going through and naming these ions. Okay, I'm moving on. I've said enough. So here you're being asked to provide the names of Mn, Mn2+, Mn3+. So the cool thing about this question, or the good thing about this question is, just by looking at it, you can tell this, first of all, this element here is a metal, right? You want to pull out your periodic table and find out where Mn is. You will see it's in the D block below the zigzag, right to the left of the zigzag, the D block somewhere there in the middle. And the metal, so number 1, it's a metal with many charges. That makes it, by this criteria, a group B metal. Oh, I can't spell group B metal. Okay. Group B metal, when you're naming them as an ion, you're going to name the element's name, as I wrote earlier. You're going to put the charge, and then you're going to write the word ion. So for this one here, Mn, this is going to be named, I'm going to name this up here. Manganese. I'm saying magna. Manganese. Manganese 2. Ion. Okay, this one here will be manganese. I'm doing it again. Oh, brain, work with me. Okay, hold on, y'all. Manganese 3 ion. Okay. And then, of course, here it's saying provide the formula. You can tell once again, these are metals, and these metals have 2 different charges, right? So nickel 2 plus, nickel 3 plus. And please notice nickel is nickel, not like the nickel coin. Okay. Okay. We talked about polyatomic ions. These ions consist of more than one atom. It shows you right here. This contains 1 nitrogen and 4 hydrogens. This contains oxygen and hydrogen. So it's called hydroxide. You want to be aware of these names. You're going to be asked to produce them in a compound form. Okay, so I wanted to make sure, at least with the first video, I was done naming ionic compounds. Okay. So what I'm going to do here, I tend to create a chart in my face-to-face class. So I'm going to go ahead and create a chart and use the chart to actually name the ionic compounds. I'm going to do that right here. And then instead of going through line by line, I'm going to be summarizing. Wait, what happened to my added page? Oh, okay. So I'm going to do this, okay? We are naming compounds. Okay, since I'm creating a chart, guess what? You want to create a chart too. We are creating compounds. We're creating compounds. Well, we're going to have the compounds, the formula, and then we're going to name them. And I'm going to focus on naming the compounds for right now for this lesson. Then in my next lesson, I'm going to be talking about how to, we did the crisscross before, crisscrossing ions to make the compounds. I want to talk about that when I do a special session for the labs, okay? I think I'll do one just for the labs to help you guys complete the lab. Okay, naming compounds. The first thing you want to do is ask yourself, look at first element. So what I do to judge a compound, for the most part, this doesn't work 100% of the time, but at you guys' level, this is very helpful. Look at the first element, because the first element tells you a lot about what to expect in the formula and then how to name it. So is the first element a metal? And if it's a metal, is it followed by a non-metal? So do you have a situation where you have a metal, comma, non-metal, okay? The other possibility is going to be a non-metal followed by another non-metal. So non-metal on non-metal, okay? Remember, metal and non-metal, these make ionic compounds, okay? And then non-metal on non-metal, these make molecular compounds, okay? So I want to focus on ionic compounds for right now, because molecular compounds is a whole different style, okay? With ionic compounds, if you have a group, hold on a second. I'm trying to think of how I should introduce this. Yeah, I would say if it's a group A metal, then you're going to have ionic A compound. So I realize your book also calls it type 1 ionic compound. I'm like, We're talking about ionic compound or illnesses. Okay, ionic A, or your book calls it type 1. Remember, this ionic compound has a fixed charge. It only has one type of charge, okay? These are all the rules about this. So when you're naming ionic A compounds, this is gonna be your template. You're gonna look for this format in the way it's named, okay? The template will be element, and then anion. Okay. The metal will be named as an element. And then the anion will be the non-metal. Okay. And so the name should usually just have two components, two parts. The first name will be the element, second will be anion. Okay, now we're looking at, let me try to make this longer here so I can have room to write. We're looking at ionic B compound. Your book also calls this type 2. And this one here has variable charge. Okay, and here's the format for this one here. It's the format that we see. It's the element, charge, anion. So you have metal, non-metal. Okay, remember, when you decide that you have a group B metal, hold on, group B metal, then this is the path you want to take. You want to go to the right, okay? So you're looking at your compound. Your goal is to name compound. You're looking at your compound. The first thing you look at is your first element. What does it tell you? Because you're trying to make a decision. In my nomenclature, I'm going down this path. Do I take a left turn or a right turn? The left turn is if your first element is a metal. The right side or right turn if your first element is non-metal. And so I'll go through and name this on a different slide when I get to it later on. My goal for this video is to name these, to use these parts right here and name these two, okay? Just to do this part of the chart. This part here has other branches, and I'll get to that later on. Okay, so before I actually get into naming this and following this format, I want to make sure I go through all of this here. So in ionic compounds, these are compounds in which ions, once they are made, are held by ionic bonds. Remember, there is stability in the ionic compound, and it depends on the interaction between the positively and negatively charged ions. For example, sodium ion, remember sodium metal loses 1 electron to make sodium ion. Chlorine gas gains an electron to form chloride ion. And then these, because they have opposite charges, are drawn to each other to form sodium chloride. What forms the bonds and keeps them together is the interaction, the attraction between the oppositely charged ions, the cation and the anion, okay? So once you made the compound, we're told that the formula of the ionic compound follows certain rules. You want to make sure that you take enough of each ion to make sure that you have a neutral compound, okay? Compounds are neutral, okay? So when we're crisscrossing the charges in the ions, we're trying to make sure we're using enough of each to make a neutral compound. So while we're here, let me detour a little bit, because I think I may have mentioned this before, but I feel like it's worth mentioning again, okay? For example, let's look at aluminum and oxygen. Aluminum being in group 3 forms a charge of 3+. Oxygen being in group 6 forms a charge of 2-. Our goal is to make a neutral ionic compound. Oh, okay, I capitalized, I have a habit. Okay, it has to be neutral, and it's ionic because we're using ions to make the compound. okay? The neutral part is implied, okay? So the proper way to do this is just crisscross this down, bring the 3 down, bring the 2 down. The charges get dropped, right? Charges, you know what I mean? The signs get dropped. Like, this is not a court case. Okay, Al2O3, and this is the compound. But what exactly does this mean? This is just saying to make a neutral compound, you need 2 Al3 pluses and 3 O2 minuses, okay? So if I were to write it down mathematically, I'll say Al3 plus, Al3 plus, O2 minus, O2 minus, O2 minus. You can see when I add up the charge here, I get 6 plus. When I add up the charge here, I get 6 minus. Remember, our goal is to combine these two to make electrically neutral compound. And we have done so. So if you're ever wondering why the zigzag thing works, it works because it ultimately tells us how many of each species or each ion is required to make the compound, okay? So once we make the compound, that one compound is called a formula unit, okay? Hopefully that explains what, if you had questions about that. Now moving on to, it says writing the formula of the ion compound, balance the charges. We kind of did that already. Yeah, in writing the formula, the cation is written first, the anion is written second. You want to make sure the subscript shows that the charge in the end is balanced. So, oh, I forgot I had this whole page here. Okay, so we're going to do this, right? Now remember, the cation has to be written first. So for this one here, this metal produces this cation, Na+. This produces this cation, Ca2+. Now remember, the charges of the positive ions correspond with the group number. Aluminum Al3+, magnesium Mg2+, aluminum again, Al3+. It's the same cation, so it's the same charge. And these ions have fixed charges, okay? Okay, over here, the anion is negative charge. So I was looking at the cations. Now the anions, once again, group number for negative charge, group number -8. So this is 7 minus 8, -1, F minus 1, O2 minus, O2 minus, what's this one here? Group 5, P3 minus, okay? Okay, to make the ionic compound, I'm going to crisscross these. Usually if the charges are different, which they have to be different, right? Because opposites attract. But the numbers before the charge are the same, they drop off. Okay, so this comes down here. It really technically drops off because the numbers are the same. The charges are different. And we end up with NaCl, right? The 1 and the 1 here cancel also. They're implied. Oops, NaCl. Okay, this one here goes down. The charges go away. This one goes down. When I say the charge, I mean, you know, the sign, the positive negative sign. Ca, instead of putting the 1 here, the 1 is implied, so I don't put it there. And then F2. This comes down here. This goes down here. Al2O3. Okay. This goes down here. This goes down here. So you don't write Mg2O2. This drops off and we end up with MgO. So that's the answer, not that. Okay. And then here, once again, this goes down here. So instead of writing Al3P3, these drop off and we end up with ALP, like the Alps. I'm not a skier or anything, but I'm thinking the Alps. Okay, now we're writing the ionic compound, but we're dealing with polyatomics. Ooh, okay. So we have polyatomics and ions. So what happens here, like before, put the 3 down here, put the 2 down here. But this is tricky because we have a 3, a pre-existing 3 in the subscript, right? So you will write Al. This 2 comes down here, this 2 in front of Al. And then for the CO3, you write CO3. Since we have a 3 here and want to add a 3 on the bottom, you don't want to write like this because it looks like CO33. So you put parentheses around this. So it looks like that. So what you're saying is to get a neutral compound, you need 2 ALs, right? Each of them 3 plus, AL 3 plus. And then 3 CO3s. Each CO3 is 2 minus, CO3 is 2 minus, CO3 is 2 minus. So the charges here are 6 plus, that'd be 6 minus. Yep, that works. Okay, so that's what we're trying to communicate. We're not saying we need 33 oxygens. No. For this next one, we have this goes down here, this goes down here. NH4, put parentheses here because you're going to bring a 2. And then CO3, no need for parentheses because the one that you put here, it drops off. So the parentheses become redundant. Okay. Okay. And then we have additional exercise here where they have us working this out for, okay. They want us to write the formula for these. So it's essentially NH4 plus combining with Br minus. The charges are the same, but opposite signs. Just consolidate them, NH4, Br, one of each, right? And then for NH4 plus and then S2 minus, remember, because you're bringing the 2 down here in front of the 4, you want to use parentheses to shield the 4 from the 2 so it doesn't look like it's NH42 and then S, okay? So these are our answers right here. Okay. This is just showing you how to write the formula from the name. So if you're given aluminum oxide as the name, aluminum came from the element aluminum. So you see this in the periodic table. Oxide came from the element oxygen. So remember, based on the group number, aluminum will be in group 3, oxygen will be in group 2, and when you crisscross these, you get the formula Al2O3. So I just kind of walked you through how they did this. They have an error here. They said nitride, but they put a nickel. I don't know what's up with that. Okay, so for barium nitride, see, barium is Ba2 plus. Barium is Ba. It's in group 2, so it's going to be 2 plus. Nitride is 3 minus. It's in group 5, so it'd be 3 minus. And then crisscross these to get the formula. So it would be Ba3 and 2. Sorry, in the time of the night. Okay, I have a trash can right there and a box of Kleenexes just in case. Okay, so I'm still naming ionic compounds. Oh, now we're naming ionic compounds. These are ionic B compounds. So please notice all the names I was looking at here, these were all ionic A compounds, right? We're trying to write them down and we're going to be naming them. Now that I think about it, we haven't even named these. Okay. Oh, they do have a summary here. Oh, we finally named them here. Okay, so we're moving on to naming ionic A compounds. So remember, ionic A compounds has to follow. We're learning how to write the formulas, right? Ionic A compounds have to follow the theme or this template. So let me write this here. Ionic A, element, anion. Okay, now the anion can have 3 possible suffixes. It can be IDE with no oxygen, 8 with more oxygen, 8 with less oxygen. Okay, so let's go ahead and look at this one. So on this first one here, you have LiBr. We know Li is the metal, so it has to be named like the element. You want to look at the periodic table and find lithium. So hold on for a second. Let me see if I can find. Okay, I went ahead and pulled up a periodic table and I'm hoping this is going to help us with the process of nomenclature. Let's see. So going back here, we're starting with, you're giving this formula right here, LIBR. Now, I don't want you guys to go and Google it. I mean, you could, but you're not going to be learning how to name it. So you look for the symbol LI, and LI, wait, hold on a second. This is supposed to be a little easier than this. Li happens to be there, and the name is, hopefully you can see that, lithium. Let me make it slightly bigger. Yeah. What language is this? Okay. You know what? Hold on a second. Okay, so I'm going to start naming the first compound. So you want to look for the symbol on the periodic table that has Li, and Li is right here. So you write the element name as is, and this would be lithium. And then look for the symbol Br on the periodic table. Let me see if I can bring this a little bit. And then bring this whole thing a little higher. Scroll over here. Br is right there. And remember, you want to take bromine and make it into bromide. Okay, so this is going to be lithium bromide. There. Okay, and I don't want to scroll too much because I do have a lot going on here. The next one we have MgI2. So you want to write the name of the first element as is. So Mg, let's see, Mg is somewhat to the left. There it is, magnesium. You want to write it as an element because remember, the first element is named as an element. Then the anion, for this one here, you want to write it as I2. Remember I2, we need two of those to make a neutral compound. So you're looking for I. I is right there. And since this anion comes straight from the periodic table, it doesn't have an additional nonmetal to it. You will write it as iodide, magnesium iodide, okay? And that gives you the second name here. Okay, I'm just trying to show you how they got the names. In the third one, you have Ag3N. Once again, look for the name for Ag. Ag is right here, but isn't this the D block? Don't elements in the D block have more than one charge? That's true, except for silver and zinc. Silver and zinc only have one charge, so you only write the name as is. So even though silver is ionic B, you will name it like it is ionic A. So you write here, it's named silver, and then move on to naming this, okay? N is right here. So nitrogen, you write it as nitra, and then you add IDE. If you have forgotten how to get these, go back to that list I gave you guys earlier. Go back here, way, way back. Remember the list I gave you? I know. This nomenclature chapter appears easy, right? It's just naming. It's not that simple. And you want to get the names from here. So I would suggest if this is tough for you, you want to write these down, and that way you keep referring to it, okay? After a lot of work, I finally had them in my head. Well, it happened before college for me, okay? So let's see, where am I? I am, oh, wait. I've lost my place right here, okay? The next thing I'm gonna be doing is MnCl2. With MnCl2, Mn is manganese. Manganese is actually a metal that has many charges. So we need to know the charge of manganese. Well, looking at this, I can't tell what the charge of manganese is. Remember how we made the ionic compound by crisscrossing? We have to do a reverse crisscross. So I usually say crisscrossing is like doing this. Reverse crisscrossing is the opposite. It's kind of like a dance move. Crisscross, reverse, crisscross, reverse, okay? So I'm gonna reverse. Remember, the nothing here is essentially 1. I'm gonna reverse that back here and then give it a negative charge because the second ion is always negative. Take the 2 and place it back up here and give it a positive charge. So essentially end up with Mn2 plus and Cl negative, okay? Now I have to name this. Mn is manganese right here on the screen. So that's gonna be manganese. manganese. I did find this time. Yay to me, kudos. 2, because of the charge. Then name this as an anion. Where's Cl? Cl is right here. Name it as chloride. So manganese 2 chloride. Okay. It takes practice to be better at this. So what I'm going to do here is I'm going to stop here because it'll make the video extra long. And then I'll do a short one. Actually, let me see. Hold on. I'm going to stop here. And then what I'm going to do next is record a session for the lab, just to give you guys a clue on how to work on the lab. And after that, I'll actually go back and work on the molecular part of the lab, okay? So let me go ahead and stop this right